So let's continue. Until now, the filters we have been talking about, they were actually performed in the visual domain. So you see exactly what they do, or you can actually understand what they're doing, just waiting the neighborhood of pixels. But now I'm going to switch into frequency space filters. And as I mentioned in the beginning, we have the low and high pass filters, and they are related to different frequencies in the images. And to do this, we work mostly with the Fourier transform. And the Fourier transform is here now expanded into 2 dimensions. Normally, you only have one frequency, but now you have 2 spatial frequencies along the 2 axes. And it looks essentially the same, except for the minus sign here and the weighting for the inverse transform. So you can go without losses, more or less, between the spatial domain, frequency domain, and back again. This equation looks ugly, and it's not so fun to implement. And good thing is people have implemented a fast Fourier transform, which is a technical solution. And the fast Fourier transform is part of many packages, so you definitely don't have to implement that one. Yeah, so in practice, you apply a couple of functions that are available now in our case in Python, and then you get this transformation. Some mathematical features that are relevant for the Fourier transform is we have the addition of signal A plus B is the same as the summing of the Fourier transform of A plus the Fourier transform of B. So if you have a signal, so I'm now showing it in 1D, if you have a signal with low frequency, signal with high frequency, and sum them, it looks something like this. It's not so easy maybe to see what they are actually doing. Looking in the Fourier space, you have a very clear peak for the frequency, and a property of the Fourier transform is actually you have positive and negative frequencies. And in principle, if you have real valued functions, then it's symmetric. It looks the same on the positive and negative side. So if you have low frequencies, they are close to the center of the plot. If the frequency increase, they go more and more out in the sides. And in the sum, you see now that you have the 2 narrow peaks and the 2 wide peaks. They are summed up, so you have this little fork here in the Fourier spectrum. This is, again, something that 1 brown and 3 blue are showing a lot of nice animations about. So if you want to take a look at that one. For our case, the interesting thing is the convolution. As you saw before, the convolution is an integral of the neighborhood for every pixel. And that can be a bit messy, in particular if you have large kernels. We tried with the separability to reduce the computational effort. But if the convolution kernel is very large or very complicated, it's actually easier to do this operation in the frequency space, because here you have the Fourier transform multiplied by the Fourier transform of a signal, and going back, or the other way around, if you do the convolution in the Fourier space, it's the same as a multiplication in the real space. So these are nice features of the Fourier transform that we're going to use. And looking at noise in the Fourier space, we have our image and we have some noise. We add the noise, and you can see that this one is noisy. Looking in the Fourier space at this image, you see the Fourier transform of the image is very much centered in the middle. You have very large flat areas, so you have lots of energy at this, close to the 0 frequency. And then there is some blurry cloud going out from it. The noise in the Fourier spectrum looks as noise again. So it's actually, if you have white noise, it means that the noise covers all frequencies, and that's why you have a constant level with some ripple. And if you add those two, you see that the effect of the noise is becoming a bit more dominant out in the quadrants, and less so at the zero frequencies. And that you can see here, that the noise has essentially buried everything information you had in your image before. And then even for the zero frequencies, it tapers off. So the signal to noise ratio for higher frequencies is less good. Now, looking at the convolution in the Fourier space, let's look at a very simple filter. The basic idea is we want to reduce the noise, and the noise is located at the higher frequencies, or the impact of noise is more dominant in the higher frequencies. So what we do, we create our filter window. Everything outside of this circle in the frequency space is rejected, and that means we cut all the high frequencies. And if we look at the multiplication of the two, it looks like this. So you have zeros, and in here you have some image information. And we look at this image, you see that the noise has become more grainy, and it's actually also reduced to some degree. I actually didn't plot did a signal to noise ratio measurement here, but that could be an interesting exercise. And the implementation of this is, just to go through that a bit, maybe I should make it a bit larger now for you. Oh, yes. Hope that's best visible. So what we do is we have our image, which is noisy. We apply the two-dimensional Fourier transform, which is in the sub-package FFT. Then I apply something called FFT shift. This is something to use because the fast Fourier transform actually organizes the data a bit strange. So it has the zero frequency up in the corner, and then a little bit, so the low frequencies are in the corners. And FFT shift is permutating everything so that you have the zero frequency in the middle. And that is needed to apply these filters, otherwise your filter kernel looks a bit weird. Yeah, I think, yes. Another way is also to apply a Gauss window, and interesting with the Gauss function is that it actually has the same shape in the Fourier space as it has in real space, just the width of it changes. And here we apply, we again have our noisy image, we apply the window, you can see how it tapers off. It actually covers a large extent of the frequency space. And when we apply it, you have, again, this smooth image, not as distinct as we had it before, but more tapered off, which is gentler to the filtered image. So here we have less of this coarse grain, but still some graininess. But that is to be expected from a convolution anyway. More fancy things is filters with band characteristics. They are actually not so easy to implement in real space. And here we look at a filter window, which is this cross. So we are looking at frequencies very close to the zero frequency. And then the effect of it is maybe not as we would wish, but just to demonstrate that you can actually tailor your filter very wildly with this kind of filtering. The effect is that you essentially see the cross effect, so you get a textile-like texture in the filtered image, which is not ideal, but just to demonstrate that you can actually do this kind of tailoring in the frequencies. A practical example of it is also the Wiener filter, which is optimized filter to balance the noise contribution against the signal contribution in the image. And this looks a bit complicated. So we have here a Fourier transform of the point spread function. So actually with the Wiener filter, you can even bring in the effect of the blurring you got from your imaging system. And then you have the power spectrum of your signal, and you have the power spectrum of your noise. And all this, a bit complicated right now, but in principle you can use this part here as a deconvolution to deblur images, something that easily gets unstable, so it's not always so easy to work with. But now on the next slide, I'm going to reduce it a bit, so we take out the effect of the blurring and only have the signal and the noise level. So we are assuming now white noise, and then this one goes down to just a constant. So in this case, if this power spectrum of the signal is much greater than sigma, then we have a filter effect equal to 1. If the power spectrum is much less than sigma, then we go towards 0. So that means, let's see. I hope I have it on next. Yes. So, well, I didn't show it the way I actually wanted to. But anyway, here you can see the filter, the Fourier transform of the image. And this would be the filter kernel now, which is now optimized for the particular signal that we are working with in this image. And then you get this kind of filtering. It's a bit stronger filtering than before, so it's more blurring, but that is what this particular tuning did to us. Here I actually had a very strong filter factor, so we could let's see. No, I can't run it now, because then I have to go back many slides. But anyway, I got some denoising effect, and in some cases, the Wiener filter is actually a good solution for the filtering. A further interesting feature of the Fourier transform is that you can actually filter different orientations in the image. So looking at images with different stripy patterns in them, here you have at 0 degrees, 30, 60, and 90. If you compute the Fourier transform of these images, you can see that you only get these dots, which correspond to the spatial frequencies. And that's clear because you only have a single frequency in here. The interesting thing is that when you start tilting this pattern, also the line going through the two frequency spots actually is also tilted. So here you see the 30 degrees, 60 degrees, 90 degrees. So you can actually determine which main orientations you have in your image. And that can be used, for example, to remove if you have some stripes in your measurement. That can happen that the detector does something strange or interference in your image. And that can then be filtered. If you can identify these frequencies in your image, then you can actually filter it by using bandpass filters that target just these spots, or these spots plus a little bit. And that is something I did in this example, where I had a projection with all these stripes in them. And these stripes, they introduced ugly bias patterns in the reconstructed tomographies. So what I did, I computed the Fourier transform of the image, created, tailored filter kernel to apply on it. And after doing this kind of bandpass filtering, I got less stripes in the projection, and that actually did something good to my images. At today's light, we may not see it, but you may see that there is some cloudiness outside and also inside of this sample. And if I ran this stripe filter on top of it, then all these stripes were actually removed from the reconstructed slices. So it was actually a successful practical example of how this stripe filter can be used. So it's actually a multi-step process where I first did this filtering and then I applied, yes?
Is this technique ever used just to quantify orientation rather
Yes.
than correct it?
Yes. So there is something called it started out before the machine learning, but in pattern analysis, there is something called Gabor filters, which actually is a sequence of filters that target different orientations, different frequencies. So yes, indeed it's used. And nowadays it's also actually used in the machine learning. In principle, that is what machine learning does in the convolutional nets. It looks at different frequencies and different patterns extracted from these. So, yes. If it's done in the Fourier space, probably not in the convolutional networks. That is too much overhead to do the Fourier transforms too. Then they also have smaller kernels. But the concept of doing bandpass filtering targeted on different orientations is very much used. And then, of course, we have some functions here in Python. So we have, for example, in SciPy, we have NdImage, which provides convolve and median filter. You also have these in scikit-image. Then we have in NumPy, we have the Fourier transforms in 2 dimensionals, the forward and inverse transform. And then we have this FFT shift, rearranging the data. One more thing, the Fourier transform is working with complex numbers, so you may have some use of these functions too, to compute the absolute value, the angle of the components, and also real and imaginary parts. So next part is about scale spaces, and until now we have only looked at images in the scale that we get, but you saw already that there is, for example, this spatially correlated noise, and that is sometimes tricky to get rid of. If you just have a convolution, maybe you need a very large convolution kernel. And the idea is actually to do some downsamplings of the image and do filtering in different levels. And by that, you can improve the filtering quality. And one way of doing it is a large mathematical framework called wavelets. And that is a transform that splits the image or the signal into 2 parts. One is a trend, so that's the low frequency part, and one is the detail, and that's the high frequency part. This splitting is done with different base functions, and there are catalogs with different base functions and in size and also in how the shape is. And these base functions are called wavelets because they have some wavy rippling effect. And applications of the wavelets one is, of course, the noise reduction, but it can also be used for the analysis. It's, for example, used in electrocardiogram analysis to see different features in them. It's used in seismology to analyze different seismic events. Then it's also used for segmentation. And a very great area is compression. So, for example, the JPEG compression is based on the wavelet theory, and you will soon see some effects that actually you can see in the JPEG compression compressed images if they are heavily compressed. But looking at it more visually, we have this test function which has some ripple on it, the noise, and when we apply a one-dimensional wavelet transform, we get the trend, which is actually shorter. So the signal length is actually halved, so that's the scale part. And then we have the detail, which more or less looks like the noise. And then we can repeat this several times. And when we have done it a couple of times, you see down here that it actually looks like a sine and, well, maybe a square wave. And, and then we still have some noise on it. Now, doing it for images, we have two orientations, and that's also giving us 4 sub-images instead of 2. So we have the combinations where we have the horizontal trend and vertical trend, and here you have vertical trend and detail for the horizontal part, and then you have all the permutations here. And when you do the wavelet transformation, you have an original image, and then you get a trend with vertical, horizontal, and diagonal trends. No, details, sorry. And downsampling again and downsampling again. And if you apply that to a test image, again, the light is not with us, but I have this test image with a lot of different features in it. It's different orientations, different intensities, and well, the diagonal detail is very hard to see for the larger scales, but when we come down here, we start actually to see all the horizontal features, the vertical features, and if the light was with us, we would even see the diagonal features. And that gives us a framework for applying filtering, and in principle for doing noise reduction. We do this decomposition where we look at the trend and we have the detail, and what we do in the very simple filtering is we just put the threshold in the detail. All signal peaks that go beyond this threshold, they are kept, and the other ones are rejected. And so after the thresholding, we get maybe something like this, and then we do the reverse transform, and we come back to original signal size, and you can see that we actually removed some noise through this. And here we have an example. I have a very noisy image with linear streaks and linear artifacts, etc. And after denoising with this approach, you can see that I definitely got a noise reduction. What you also see are these little artifacts, small ripplets, and that is something you also see, for example, in very heavily compressed JPEG images. So this is one way, a very simple wavelet-based filter. There are more advanced ones, but that would be, again, a full lecture probably, or even more on just that topic. Then a next step, people started thinking about, with the wavelets you can do this kind of scale work, but can we actually express it instead with the differential equation framework? And yes, and for this we have this original image, and we have different types of filter that I'm going to show you. I have a diffusion filter, and I have also a inverse scale space filter, which is a regularized filter. And the reason for using these is that you saw already that the convolution filters, they introduce blurring, and we don't want blurring. We want to get rid of the noise, but we don't want blurring. And this is actually what these filters can do for us. So one model is to use the diffusion filter, which uses a physical model as a starting point. So In this case, it's the heat transport equation. And then we have, in principle, the temperature is the image intensity. So looking at this example here, let's just see if I can start it. We can see that it should restart, I hope. I think my slide is a bit confused right now. Yeah, there it comes. Yeah, so in the beginning, you have your image, and very soon everything blurs out to becoming a homogeneous image. And that is what the heat equation actually does. It levels out, homogenizes the temperature within the image. So this is not really useful. You get the blurring effect, but you get it way too much. So what people started doing is starting to control the diffusivity within these images. And what you want is that you have flat regions. They want a lot of smoothing. But as soon as you come to an edge, you want the smoothing to stop. So what we do is to apply a threshold function that tells that near the edges, the diffusion is 0, and in the flat regions, the diffusion is 1. And depending on how you want to do it, there are different contrast functions, but this is a typical one that is used. And here you can see that you have a threshold level and you have a steepness control, and that gives you control over how the filtering is working. And if we apply that to this test image, you can see that the diffusivity map is in the flat regions is white, which means 1, so full diffusion. And near the edges, it's getting darker, so no diffusion at all. There are regions which are more diffuse what it actually is, so then you also get some gray level in between. But the problem is that when you compute the gradient, you're noise sensitive, and you don't want that. So what we do is we actually apply a smoothing to this gradient, and that levels out the noise effects, and then finally we can compute the full diffusion filter. And here you can see the effect of that one running. It goes a bit slow in the beginning, but see if we can start it. So, but you can see here in the beginning it's very noisy, and then it slowly smooths out, at least in the areas between. But the edges, they are still well preserved, and that is the goal of this. So that was the beginning of a whole category of filtering techniques. The next step is starting using it as a regularization problem, where you have one part is the bounded variation, which is in principle just the absolute gradient over the sum of the absolute gradient in the image. And then you have some fidelity term, which is the difference between original and the filtered image. And by optimizing this, you come to an equation that led to this so-called inverse scale space. It's actually compared to the diffusion filter, it's flipping the order. The diffusion filter starts with a very noisy image and trying to press it down. What the inverse scale space is doing, it's looking for the big structure and build them up to some level. And it's a very strong filter for edge preserving filter for noise reduction. And it also has a nice termination point where we can find where to stop it. So that gave this kind of equation that has a couple of control parameters. We have a regularization parameter here. We have the time step, and there is another regularization parameter down here. Applying this filter is quite powerful, and again, this one is started in the wrong place. So let's go back here. You can see that the noisy image in few steps turn into a very smooth result. And This is a filter we have been using in our group for many years now. Still, the tuning can be a bit tricky because you have 4 parameters to tune, but after a while you get the feeling of how to tune this. What is really remarkable is how sharp the edges remain throughout the whole filtering process. This is, by the way, a piece of a dried lung that we did tomography of, and the idea was to see if we can see the channels in these lungs. Yet another type of not denoising filter is non-local means, which it's like a parallel development to the PDE filters, and it's much simpler approach, bit computational heavy, but in principle what the idea of this filter is that you take regions that are very similar and filter them together, so get an average in regions that have similar properties and do the averaging between them. And that is pretty nice concept, but also computational expensive. Again, it has a lot of, I skipped that one. We look at the effects better. Then you can see here we have the original. I think that was the one we used also for the wavelet. Here you can see the effect of the filtering and the difference of it. And with the non-local means, you can get a very good smoothing effect. And also, even if you have thin lines which have high amplitude, they are still preserved, which is nice because it recognizes that you have these similarities in the image. So here, for example, it's a ring artifact, which we actually want to get rid of, but it's actually still maintained because it has these strong features that has a likeliness with other similar strong features. The complications with it is that the complexity is n squared, and it's not very feasible for 3-dimensional images unless you take to some tricks. And the trick is actually that you start looking at, instead of comparing every pixel to every pixel, you start looking in smaller blocks where you do the comparison, and then you can speed up the processing quite a lot. These filters are also implemented often in on the graphic card, so that even speeds it up further. I have produced a notebook where we can look into the details of this filter, but I think I leave that for self-study because I have a couple of more things I want to talk about today. One is actually a further development of the non-local means, which is called BM3D. It's working with something called block matching, so it's taking on the idea of how the non-local means works, but it really looks for similar regions, extracting them as block and then filtering them together. And it's a 2-step algorithm where you first do a simple pre-filtering, and from that pre-filtering you do a lot of analysis, and you can see here even the Wiener filter comes into play. So it's a pretty complex filter. I recently had some, I think it was 500 cubed images, and it took a couple of hours on a medium strong workstation to compute. So it takes some time to compute it, but the results, they are very nice. So here you see the block matching. So what the filter is doing, it has some reference region, and then it sees, okay, these regions, they look very much like the same. Let's filter them all together and bring back the result. And we tried it on some of our test images, and the most important thing is that it introduces much less blurring in the images. You can see that non-local means has some blurring. The total variation also has even more blurring. And then we have this BM4D, which actually does a very good job at filtering these images. And you can see that the noisy image is relatively low signal to noise ratio. So you can go from really bad into nice clean images. That one I skip. And on top of this, we even have denoising with more advanced methods. So going towards the machine learning based denoising, you can do a lot of training and specialize your images on cleaning up. And they use more or less the non-local means as a reference. You have also BM3D, and then there are some machine learning based images. This is a really long review paper. I think it's 30, 40 pages, where they show different types of denoisers. Some very tailored for specific problems, but others, like the BM3D, is general purpose. We have seen a large collection of different denoisers, and the question is which one to take. Taking the best is one choice, but what is the best, and what is the best for your specific images? And also, more is, do you have time to use it? If you want to process thousands of images, you can't use something that takes 1 hour per image. That would take too long time, or you have to buy a lot of computational resources to do it. And here is a list of different criteria, how to select filters. And yeah, I hope that is a guideline that can help you. Another thing you can do with filters is analyzing orientations. And when we come back to your question, this is something that is done also a lot. In this case, we want to really quantify which orientations we have in the image. And I have some examples, a very simple example, more complex with, you can see that there are some directions in them. This hair, or I don't know if it's hair or something. And then we have a peacock feather. And now we want to measure the local orientations or orientations in these images. And the first way would be to look at the gradients, because if we have the gradient in x and y, we can compute the orientation from it. And here we can see that in this region we have mainly vertical lines, and here we have mainly horizontal lines. But the gradient itself is a little bit hard to tame, because you can see if I compute the gradient on these images, you have a lot of noise in the measurement. You can see that some places that you have, of course, some orientations, but they often come in pair, that you have a plus and minus orientation. This is more obvious even in this one, where you see that there is always a ripple between plus and positive and negative angle, also in the peacock feather. So the gradient itself is a bit too sensitive to work with. We can try looking at the Fourier transform as we did before, but here it's very hard to see any distinct frequencies. In the peacock feather, we could start seeing some indications, but still it's not really easy to see something. So what is introduced for this purpose is we look at the structure tensor, which is defined by the gradients in different orientations. And with that, we can compute the eigenvalue decomposition of it. And from there on, we can start computing the orientations. As I said before, gradients are noise sensitive, so what we do is actually applying also a Gaussian filter to the orientations. This is actually even implemented as a nice function. It's called Gaussian filter, and here you can say, bring in the image, you can give a sigma, and you can say which order in which direction. So it can even compute the derivatives for you in a smooth way. So this is a nice function if you want to do that. So looking at the components of the structure tensor, looking again at the ball packing, and now you can see nicely, first of all, that we don't have very much ripple in the images, so the noise is out. And also you can see here the orientations, the local orientations, much clearer in these images. So this is a nice way to continue. And when we start looking at the eigenvalues of these, we can look at the local coherency. That means, in principle, that we can see if there is a dominant orientation or not within the image, and then finally, so that's the two extremes, that you have clear, well aligned with one of the axes, or you have something in between that's a bit uncertain. And looking at that on the ball packing, you can see that along the edges we have a very good local coherency, and in the flat regions it's more ambiguous what we have, so it doesn't come out much in that. We can also, with the help of these tensors, we can also, or tensor components, we can also compute the local orientation. And the local orientation looks now like this, where we have the original image, and now this is coded in radians. And you can see that in this direction we have more something like, it's around 45 degrees in this side, negative, and here we have positive 45 degrees. So it gives us a way to measure the local angle in the image. And then with more textured features, like the hair and the feather, we can get even more information. Here we have the hair. You can see, instead of, as we had before, we had more ripply from plus and minus angles. Now we have, in principle, clear blocks. We have a little bit of negative angles, a little bit of positive angles inside. And if we look at the histogram of this one, we get a clear peak of the distribution, local distribution of angles in this image. Can do the same also for the feather, and then we have a different orientation, and this one actually makes pretty much sense because we have a diagonal orientation generally in this image. And that tells us the average orientations in the hair is horizontal because we are around 0, and here the average is something around 30 degrees, 45 degrees or something. And then we can also compute it locally, but to compute the local orientation we need to have a sample area, so we actually do it blockwise and the analysis. And then you can see here in the peacock feather, you can see in this one we have something that is between 45 and 90 degrees. In this region it's more like 0, and in this region it's again around 45 degrees. So you can actually, in different regions, you can measure it, and then we can even quantify locally and compute, either measure it as angles locally in different blocks, or you can even do a vector field telling which orientations you locally have. So this is what you can do with the help of the shape tensor, a structure tensor, sorry. And that's one kind of already quantitative information. So in principle, the first quantification we do from our images. And finally, our time is running up, but this is also a very important question to verify how good is my filter actually. And in principle, what you need to do is to make these measurements to avoid that you alter the image too much, because with these filters, as you have seen, if you have a white kernel, you can blur everything and remove relevant information. And here we have different ways of doing a validation. The first, just visual inspection. You see its images, so you see if it makes sense or not. So that's already an indication that you're on the right track. You can work with difference images to see if the difference of the applied filter makes sense or not. That can also be quantified. And then the full test workflow would be to work with degraded phantom images and see what is the effect of changing parameter in the outcome of the filtering. And the difference images, if you have a noisy image and apply a filter, you should, in principle, just see the noise. That's rarely the case, because often you have some oversmoothing, and then you can see around the edges that you got some blurring, and the edges shine out. If your filter introduce intensity scaling, you see the image once again with different intensities, but that is also an indication that something is wrong. When you implement your own filters, it can even happen that you get a geometric shift. So for example, if you use even number size of the kernel, there is no clear center of it. So that means that the image is shifted up and sideways. So that is something you can see in that one too. Then we have performance testing. I call it a smoke test from electronics. In principle, when you test electronics, you push in signals of different amplitude and see if it works, if some components smoke, get overheated. What we do here is we create phantoms with relevant features for the analysis, and then we add noise, introduce blurring, and see what happens when we apply our filters and even the further processing work. And then you repeat that several times, so new noise levels, and repeat the same noise level to get better analysis statistics. And then you can see the results afterwards. So what you need is a known phantom. This is Shep-Logan phantom, which is used a lot for tomography tests. This is a structure which I made to simulate root growth in soil. So depending on your application, you can have different types of test phantoms. And also, of course, for data evaluation, you can also use all the data sets that we talked about last week. And then we need some metrics for the analysis. And one classic is the mean squared error. So you just subtract, take the difference between the two images, a square, and sum up everything. The other one is called structural similarity. It has more information built into it, so it includes even the variance and the local information. So this one was developed to test the signal quality at image or film transmission, actually, to see how similar are the images. Not only that you get a number if they deviate a bit, but this also tells really the similarity between the images. This paper here actually compares the two and shows the benefits of using these two methods. So I created a test run example where I had these phantoms, small features, larger, and big features. And then I added also noise to the images for each size. So I have sigma 1 up to sigma 10. You can see here it's barely visible. And then I ran a lot of simulations on that, and then I could see here the effect of changing different parameters on these images. And you can see clearly at some places you have a clear breakdown. All of a sudden the algorithm broke down and didn't deliver anything. And this is interesting to see where your parameter space is actually that you can work within, and if it fits your actual analysis task. We have a lot of images and filter techniques today, and here is a little overview of what these can do. And exactly which one you use depends again on how noisy your data is, how much time you have, and so on. So I did the test with different signal to noise ratio to see how the different filters behave. This is a bit small now on the screen, but you can look at it also in the slides afterwards. And well, that's the end of today's lecture. Today I talked about many filters, for denoising, but also for enhancing and analyzing structures. And which one you choose depends on what you want to do with the data, which quality requirements. Sometimes you don't need to filter that much because the following processes are able to handle it. And of course the available time, but in principle, I showed a lot of methods that can handle really bad data, but the best way is actually to, from the beginning, measure with good quality if you can. So good measurements should be preferred if you can, but in the case you can't, then we have the tools to handle it. Yes, and then also with the orientations, the filters can already provide some quantitative information. Yeah, and that was it for today.